Welcome to this video. We're going to solve some problems on circuits involving resistance, potential difference, and current. So here's an example of a circuit. Before we start on number 21, I want to state a couple of quick things. The equation for resistance, the definition is voltage divided by current. And voltage is another term for potential difference. This equation is often rewritten by multiplying both sides by current, I. And what do you get? You can confirm that when we multiply both sides by I, the equation becomes this. Potential difference equals current times resistance. This equation can be applied to any portion of a circuit. If you have multiple resistors, R1, R2, you can apply the equation to each resistor. So for example, here's some first resistor, R1, and it has some current through it, I1. Multiply those together and you get the potential difference dropped as you go through the resistor. This is a second resistor with resistance R2, and it has some amount of current, I2, passing through it. And when you multiply those together, you get the potential difference dropped across that resistor. The total potential difference that's dropped in a circuit is equal to the total current times the total resistance of the circuit on the whole. So you can even apply the equation V equals IR not only to individual resistors like this resistor and that, but also to the entire circuit as a whole. And of course, where does that potential difference come from? The potential difference that we drop in the resistors? It's supplied by the EMF. So these two things are equal. So number 21, a 1 ohm resistor, that's here, and a variable resistor are connected in series with the battery whose EMF is 10 volts. V there is for volts. The battery has negligible internal resistance. Don't worry about that just yet. The variable resistor is set to 1 ohm. So this resistor here, that symbol where the arrow goes through the box, that means you can tune the resistor to different resistances. You can adjust the resistance to a variety of values. So it's variable. Okay, right now it's set to 1 ohm. Calculate the potential difference dissipated by this resistor. Well, what's the potential difference? That's not too bad. You know that as we go around this circuit, this closed loop, the total EMF supplied must equal the total potential difference dissipated. That's Kirchhoff's second law. Energy has to be conserved. So here's the thing. The current in this circuit, all of the current passes through that first resistor. So I'll call it I1. And then all of the current passes through the second resistor, I2. The reason all of the current passes through the first and the second is there's no other branch for the current to take, and thus it's all forced through the first resistor and then all forced through the second resistor. The resistance of the first resistor we'll call R1. The resistance of the second resistor we'll call R2. And the potential difference lost across the first is V1. The potential difference dropped across the second is V2. I1 is equal to I2. And R1 is equal to R2. The equation for potential difference is V times I times R. V equals I times R. So if they have the same I and the same R, then the two resistors will also have the same V. So this V here equals this V. We'll call it just one variable V. As we go all the way around the circuit, like this, the total potential difference, the total EMF gained is the 10 volts. And what do we lose? Well, we lose V of potential difference here. We lose V. And the charges also lose another V right here. 2V on the right side. So V, the potential difference, lost or dropped across each individual resistor. That value of V is going to be 10 over 2 or 5 volts. Here's a simpler way to see the solution. Because these two resistors have the same resistance, 1 ohm for each, and because they have the same current, I, they dissipate the same voltage according to V equals IR. That means if they dissipate the same voltage, they share the EMF equally. This resistor dissipates half the EMF, and this dissipates the other half of the EMF. So each would dissipate then 5 volts. Part II. The potential difference dissipated by the non-variable... Oh, that's the same answer. Both resistors, the variable resistor, this one, and the non-variable, the fixed resistor, they both dissipate 5. What's the current in the circuit? Well, that's not too bad. You can apply the equation V equals IR to this resistor because you know its value of V, you know its value of R, and you're looking for current. So its voltage, its potential difference dissipated is 5 volts. The unknown is I, and the resistance of this one is 1 ohm. You divide both sides by an ohm, and you get 5 amps, 5 amperes. So that's how you find the current through this resistor. But the current through this resistor is equal to the current in the entire circuit, because there aren't any other branches. There's just that one branch, and so this is the total current. So 5 amps. Part B. The variable resistor is changed to 2 ohms. So now it has twice the resistance as this. Does the potential difference across the variable resistor increase or decrease? This resistor now has bigger resistance. This one now has less resistance. I'll call this resistor 1 and resistor 2. Although that's a little backwards. Let me call this one resistor 2 because it's 2 ohms, and this will be resistor 1 because it's 1 ohm. So V2, the potential difference dissipated across this, is equal to the current through it times its resistance. V1, the potential difference across this, is equal to the current through it times its its resistance. The current through this one I'm just going to call I because that's what was given. And then the current through the second resistor is the same I. So these have the same current I through them. The resistance, though, is not equal. This resistance is 2, this resistance is 1 ohm. And so clearly, V2 is 2I, but V1 is just 1I. V2 is twice V1. Because it's twice, they're no longer sharing the 10 volts equally. V2 gets a bigger share. In fact, if you work it out, V2 would be 6.7 volts, and V1, this first resistor, would dissipate only 3.3 volts. So by increasing the resistance here, not only do you increase its potential difference, but you have to then decrease this potential difference, because the total must add to 10. Okay. So that answers part I and II.